Industry professionals have shared their experiences with General Electric's fan-cooled transformers. Installers have successfully installed these transformers on multiple projects, noting that the installation process is relatively straightforward and the units are compact and easy to handle. Electrical engineers find that fan-cooled transformers offer several advantages, including improved efficiency, reduced noise, and increased reliability. However, it's important to ensure proper ventilation and cooling to maintain optimal performance. Maintenance technicians have found that the fans are easily accessible, making maintenance straightforward. Replacing the fans is also a simple process, which minimizes downtime. Feedback on General Electric's fan-cooled transformers has been positive. Professionals generally express comfort with using these units due to their reduced size and weight, having a smaller footprint and lower weight compared to traditionally cooled transformers. Improved efficiency is achieved because the fans enhance cooling, resulting in reduced energy losses. Lower noise is another advantage, with fans operating quietly, minimizing noise pollution. The advanced cooling systems enhance the lifespan of the transformers, thus increasing reliability. Ease of installation and maintenance is also a plus, with straightforward installation and accessible fans simplifying regular maintenance. However, it's important to consider several factors when using fan-cooled transformers. Firstly, adequate ventilation is crucial to ensure proper cooling. Secondly, transformers should be protected from excessive moisture, dust, and corrosive gases, taking into account environmental conditions. Thirdly, ensure the power supply meets the transformer's fan power requirements. Lastly, regular inspections and fan replacement may be required over time for maintenance. General Electric's fan-cooled transformers offer several benefits over traditional transformers, making them a viable option for various projects. As with any electrical equipment, proper installation, ventilation, and maintenance are essential for optimal performance and longevity. When selecting and installing fan-cooled transformers, several technical aspects require careful consideration. These considerations ensure the transformer operates efficiently, safely, and reliably over its intended lifespan. Here's a detailed exploration of these technical factors. Firstly, transformer capacity and loading. Selecting the appropriate transformer capacity is crucial. The transformer should be sized to handle the anticipated load plus a reasonable margin for future expansion. Overloading a transformer can lead to overheating, reduced efficiency, and premature failure. Secondly, cooling system design. The fan-cooled design relies on forced air circulation to dissipate heat. The design must account for the transformer's heat generation rate, ambient temperature, and altitude. The cooling system should be capable of maintaining the transformer's temperature within its specified operating limits. Thirdly, fan specifications. The fans used in the cooling system should be selected based on their airflow capacity, noise level, and energy efficiency. High-quality fans with appropriate ingress protection, or IP, ratings should be used to ensure reliable operation in harsh environments. The fan's motor should also be compatible with the available power supply. Fourthly, ventilation requirements. Proper ventilation is essential for the fan-cooled transformer to operate effectively. The installation location must provide adequate airflow to prevent hot air from recirculating back into the transformer. Ventilation openings should be sized to meet the cooling system's airflow requirements. The location should also be free from obstructions that could impede airflow. Fifthly, environmental protection. Transformers should be protected from environmental factors that could degrade their performance or lifespan. This includes protection from moisture, dust, corrosive gases, and extreme temperatures. Enclosures with appropriate IP ratings should be used to provide adequate protection. The enclosure material should also be resistant to corrosion and degradation from environmental exposure. Sixthly, noise levels. Fan-cooled transformers can generate noise due to the operation of the cooling fans. The noise level should be considered, especially in noise-sensitive environments. Low-noise fans and vibration dampening mounts can be used to minimize noise pollution. Noise barriers or enclosures may also be necessary in some cases. Seventhly, power supply requirements. The fans require a power supply to operate. The power supply should be reliable and capable of providing the required voltage and current. Overcurrent protection should be provided to protect the fan motors from damage. The power supply should also be properly grounded to prevent electrical hazards. Eighthly, maintenance and monitoring. Regular maintenance is essential to ensure the continued reliable operation of fan-cooled transformers. This includes periodic inspection of the fans, cleaning of the cooling fins, and testing of the installation. Monitoring systems can be used to track the transformer's temperature, load, and other critical parameters. Alarms can be configured to alert personnel to potential problems. Ninthly, standards and codes. Fan-cooled transformers should comply with applicable industry standards and codes. This includes standards for transformer design, performance, and safety. Compliance with these standards ensures that the transformer meets minimum requirements for safety and reliability. Examples of relevant standards include Institute of Electrical and Electronics Engineers, or IEE, C57.12.0 for liquid-filled transformers, and National Electrical Manufacturers Association, or NEMA, standards for enclosures. Tenthly, installation practices. Proper installation practices are crucial for the safe and reliable operation of fan-cooled transformers. This includes ensuring that the transformer is properly supported, that all electrical connections are made correctly, and that the cooling system is functioning as intended. Installation should be performed by qualified personnel who are familiar with the transformer's design and operation. Furthermore, consider the following factors in greater detail. Firstly, detailed ventilation design, which involves a comprehensive analysis of airflow patterns, heat dissipation rates, and ambient conditions. Computational fluid dynamics, or CFD, simulations can be used to optimize ventilation design and identify potential hotspots. The design should ensure that the transformer's temperature remains within its specified operating limits under all expected conditions. Secondly, advanced fan control systems incorporating variable frequency drives, or VFDs, can be used to optimize fan speed and reduce energy consumption. The control system should be able to adjust fan speed based on the transformer's load and temperature. Advanced control algorithms can also be used to minimize noise and vibration. Thirdly, enhanced environmental protection measures, such as conformal coatings and hermetically sealed enclosures, can be used to protect transformers from harsh environments. These measures can significantly extend the transformer's lifespan and reduce maintenance requirements. Fourthly, predictive maintenance techniques, employing advanced sensors and data analytics, can be used to predict potential failures and schedule maintenance proactively. This can minimize downtime and prevent costly repairs. Fifthly, harmonic mitigation strategies involving the use of filters or other techniques can be used to reduce harmonic distortion in the transformer's output voltage. Harmonic distortion can lead to overheating, reduced efficiency, and equipment damage. Sixthly, surge protection devices, or SPDs, should be installed to protect the transformer from voltage surges caused by lightning or switching events. Voltage surges can damage the transformer's insulation and lead to premature failure. Seventhly, grounding and bonding practices must adhere to the National Electrical Code, or NEC, requirements to ensure electrical safety and prevent ground faults. Proper grounding and bonding can also reduce the risk of electromagnetic interference, or EMI. Eighthly, fire protection systems, such as automatic sprinkler systems or fire-resistant enclosures, should be considered for transformers installed in critical locations. These systems can help to prevent or mitigate the spread of fire in the event of a transformer failure. Ninthly, energy efficiency optimization, employing high-efficiency transformer designs and advanced cooling techniques can significantly reduce energy losses and operating costs. Energy-efficient transformers can also help to reduce greenhouse gas emissions. Tenthly, life cycle cost analysis, considering all costs associated with the transformer over its entire lifespan, including purchase price, installation costs, operating costs, maintenance costs, and disposal costs. This analysis can help to identify the most cost-effective transformer option for a given application. The analysis should account for factors such as energy efficiency, maintenance requirements, and expected lifespan. In addition to these considerations, it's important to stay up to date on the latest advances in transformer technology. This includes advancements in materials, cooling techniques, and control systems. By staying informed, engineers can make informed decisions about transformer selection and installation and ensure that they are using the best available technology. Proper installation, operation, and maintenance of fan-cooled transformers are crucial for ensuring their longevity, efficiency, and safety. The following guidelines provide a comprehensive overview of the best practices for handling these transformers. Firstly, pre-installation inspection. Upon receiving the transformer, conduct a thorough inspection to identify any signs of damage that may have occurred during shipping. Check for dents, scratches, or other physical damage to the enclosure, cooling fans, and other components. Verify that all components are present and that the transformer matches the specifications outlined in the purchase order. Secondly, location selection. Choose a location that provides adequate ventilation and protection from environmental factors such as moisture, dust, and corrosive substances. Ensure that the location is easily accessible for maintenance and inspection. The transformer should be installed on a level surface that can support its weight. Thirdly, ventilation. Ensure that the transformer has adequate ventilation to dissipate heat generated during operation. The ventilation opening should be sized to meet the transformer's cooling requirements. Avoid obstructions that could impede airflow. In enclosed spaces, consider installing ventilation fans to improve air circulation. Fourthly, mounting and securing. Secure the transformer to its mounting surface using appropriate hardware. Ensure that the mounting hardware is compatible with the transformer's weight and size. Follow the manufacturer's instructions for mounting and securing the transformer. Fifthly, electrical connections. Ensure that all electrical connections are made by qualified personnel in accordance with applicable codes and standards. Use appropriate wire sizes and connectors for the transformer's voltage and current ratings. Verify that all connections are tight and secure. Sixthly, grounding. Ground the transformer in accordance with applicable codes and standards to protect against electrical shock hazards. Use a grounding conductor of appropriate size and material. Verify that the grounding connection is secure and effective. Seventhly, fan operation. Verify that the cooling fans are operating properly before energizing the transformer. Check for any obstructions that could prevent the fans from rotating freely. Ensure that the fans are properly lubricated and maintained. Eighthly, energizing the transformer. Before energizing the transformer, verify that all connections are properly made and that the transformer is properly grounded. Slowly increase the voltage to the transformer to avoid voltage surges. Monitor the transformer's temperature and current to ensure that it is operating within its specified limits. Ninthly, regular inspections. Conduct regular inspections of the transformer to identify any potential problems. Check for signs of overheating, corrosion, or physical damage. Verify that the cooling fans are operating properly and that the ventilation openings are clear. Tenthly, maintenance. Perform regular maintenance on the transformer to ensure its continued reliable operation. Clean the cooling fans and ventilation openings to remove dust and debris. Lubricate the fan motors as needed. Replace any damaged or worn components. Furthermore, delve deeper into the operational best practices. Firstly, thermal monitoring systems, using thermal cameras or sensors to monitor the transformer's temperature and identify potential hotspots. Early detection of hotspots can prevent equipment failure and extend the transformer's lifespan. Secondly, vibration analysis, employing vibration sensors to monitor the condition of the cooling fans and detect imbalances or other mechanical problems. Vibration analysis can help to identify potential fan failures before they occur. Thirdly, oil analysis, periodically sampling and testing the transformer's insulating oil to assess its condition and identify contaminants. Oil analysis can provide valuable insights into the transformer's internal condition and help to prevent premature failure. Fourthly, infrared thermography, using infrared cameras to inspect the transformer's electrical connections and identify loose or corroded connections. Loose or corroded connections can cause overheating and equipment failure. Fifthly, partial discharge testing, employing specialized equipment to detect partial discharges within the transformer's insulation. Partial discharges can indicate insulation degradation and potential failure. Sixthly, dissolved gas analysis, or DGA, periodically analyzing the gases dissolved in the transformer's insulating oil to detect signs of internal faults or overheating. DGA can provide early warning of potential transformer failures. Seventhly, power quality monitoring, using power quality analyzers to monitor the transformer's input and output voltage and current and identify harmonic distortion or other power quality problems. Power quality problems can damage the transformer and other electrical equipment. Eighthly, load management strategies, implementing load management strategies to reduce the transformer's peak load and prevent overloading. Load management can extend the transformer's lifespan and improve its efficiency. Ninthly, emergency response plans, developing emergency response plans to address potential transformer failures or other emergencies. Emergency response plans should include procedures for isolating the transformer, containing spills, and notifying emergency personnel. Tenthly, training and education, providing training and education to personnel responsible for operating and maintaining fan-cooled transformers. Training should cover topics such as transformer operation, maintenance, safety, and troubleshooting. Continuous education is essential to keep personnel up to date on the latest technologies and best practices. Moreover, specific procedures can enhance transformer management. Firstly, establish a preventative maintenance schedule detailing routine inspections, cleaning of cooling fans and ventilation, terminal tightening, and oil sampling, if applicable. This minimizes the chances of unexpected failures. Secondly, keep detailed records of all maintenance activities, inspections, test results, and repairs performed on each transformer. These records are invaluable for tracking performance trends, identifying potential problems, and making informed decisions about transformer maintenance and replacement. Thirdly, ensure regular cleaning of cooling fans and ventilation openings to maintain effective heat dissipation. Use compressed air or a vacuum cleaner to remove dust, dirt, and debris. Fourthly, perform periodic terminal tightening to prevent loose connections, overheating, and potential equipment failures. Use a calibrated torque wrench to tighten terminals to the manufacturer's specified torque values. Fifthly, where applicable, take insulating oil samples periodically and send them to a qualified laboratory for analysis. DGA and other tests can detect early signs of internal faults or insulation degradation. Sixthly, visually inspect the transformer regularly for signs of oil leaks, corrosion, or physical damage. Address any problems promptly to prevent further damage. Seventhly, monitor the transformer's load and temperature to ensure that it is operating within its specified limits. Install thermal sensors or monitoring systems to provide real-time data. Eighthly, conduct infrared thermography scans periodically to identify hot spots or other thermal anomalies. Address any hot spots promptly to prevent equipment failures. Ninthly, implement surge protection measures to protect the transformer from voltage surges caused by lightning or switching events. Install surge arresters or other protective devices on the transformer's primary and secondary windings. Tenthly, develop and implement an emergency response plan to address potential transformer failures or other emergencies. The plan should include procedures for isolating the transformer, containing spills, and notifying emergency personnel. By adhering to these guidelines and best practices, organizations can maximize the lifespan, efficiency, and safety of their fan-cooled transformers. This translates to reduced downtime, lower maintenance costs, and improved overall system reliability.